Welcome to This Explainer. Today, we're embarking on a pretty fascinating quest. We're going to dig right into the numbers and set out to find the true center of the data universe. Now, you might be thinking, finding the middle of something, that's simple, right? But as we're about to see, the mathematical reality of finding the middle is packed with nuance, competing strategies, and some really dramatic differences.
Let's kick things off with part 1, finding the center and the two tools for the job.
So to find that center, we have two main statistical protagonists, the mean and the median. Now, when we talk about the center of a data set, we're really just talking about the mathematical middle. But here's the fascinating thing. Even though both of these tools are looking for that exact same elusive center point, their unique mechanics mean they describe it totally differently. One looks at the sheer weight of the numbers, while the other, well, it looks purely at their position. And honestly, that distinction changes literally everything.
All right, let's dive into this with part 2, the mean, averaging it out. If you've ever, say, calculated your grades at the end of a semester, or figured out the fuel efficiency of your car, you've probably used this one. Most of us just call it the average. The mechanics of the mean are built on a classic, super reliable two-step formula. Step 1, you add every single value in your dataset together to get one big total. And step 2, you take that grand total and simply divide it by the total number of individual values you collected. It's actually a highly democratic process. Every single number, no matter how big or how incredibly small, gets to contribute its exact value to the final result.
Okay, let's look at our first piece of evidence. Take a glance at this data set. We've got the numbers 2, 4, 6, 8, and 10. This is a peaceful, perfectly symmetrical data set. The jumps between the numbers are totally even. So, let's run our simple math on this data. Step 1, we add them all up. 2 plus 4 plus 6 plus 8 plus 10, that gives us a total sum of exactly 30. Step 2, we take that 30, and since we have 5 individual items in our data set, we just divide 30 by 5. That simple division gives us our center point. And the result? It's exactly 6. For this well-behaved, totally orderly data, our mean is exactly 6. It sits perfectly right there in the middle of our numerical spread. Clean, mathematically sound, and incredibly intuitive, right?
Now let's look at the other side of the coin in part 3, the median, the middle ground.
So the median, it operates on a completely different frequency. It totally ignores addition and division in favor of one absolute rule. It acts as a physical divider, perfectly splitting your dataset right in half. It is the exact point where 50% of your values sit neatly below it and exactly 50% sit above it. It doesn't care at all how massive or tiny the numbers at the extreme ends are. It literally only cares about what's standing right in the center of the room.
Finding the median requires a different set of steps. Step 1. And listen, this is absolutely crucial. You must sort the data from lowest to highest. If you skip this, the whole thing just completely falls apart. Step 2. Once everything is lined up in perfect order, you simply walk down the line and pluck out the one value that sits dead in the center.
Let's apply this positional strategy to our perfectly symmetrical data set from earlier. We've got everything lined up in order, 2, 4, 6, 8, 10. And just looking right at the sequence, the number 6 sits perfectly positioned in the exact middle. 2 numbers are to its left, and 2 numbers are to its right. So here, in this perfectly symmetrical world, both our mean and our median completely agree.
Now, you might be wondering, wait, what happens if I have an even number of values and there's no single middle number to just pluck out? Well, the rules are just as simple. You just find the 2 middle numbers and take their average. So look at the sequence 1, 3, 5, 7. We grab the 3 and the 5 from the middle, add them up to get 8, divide by 2, and they average out to a median of exactly 4.
But things aren't always so perfect. That brings us to part 4, the outlier effect, when data goes wild. It's time to introduce the real villain of our explainer, the outlier. Notice the contrast here. On the left, we have our normal, perfectly balanced data. But look at the outlier data on the right. We have a quiet, steady little sequence of 1, 2, 3, 4, and then suddenly, boom, a massive anomaly crashes into the set, the number 100. Let's see exactly how our two statistical tools handle this absolute chaos.
Now, what's really interesting here is what happens to our highly democratic mean. Remember, the mean has to count everyone's exact value. So we add 1, 2, 3, 4, and that massive 100, which gives us 110. We divide by 5, and suddenly our mean gets completely dragged upward to 22. Think about that. In a data set where 4 out of 5 numbers are literally between 1 and 4, the mean is telling us the center is 22. It is highly, highly sensitive to extreme values.
But contrast this immediately with the median. We line up our data, 1, 2, 3, 4, 100. The median walks down the line, totally ignores the towering ridiculous size of that 100 and just points to the middle position. And that middle position? It's 3. The median completely ignores the extreme value and holds its ground firmly at 3.
So this crucial point is summarized perfectly in this side-by-side showdown. Faced with the exact same data, the mean shifts dramatically to 22, getting pulled violently upward by that extreme value. Meanwhile, the median remains perfectly stable at 3. This proves a vital statistical principle. The median reflects the quote-unquote typical value far better when extreme outliers exist in your data. Which brings us to part 5, choosing the right tool, practical applications.
Understanding the math is fantastic, obviously, but translating that math into reality is what truly matters. This visual cheat sheet shows us exactly when to deploy each of these distinct mathematical tools. If you have symmetric data, the mean is absolutely your go-to. But notice how often the median takes over. For data with outliers, skewed distributions, and especially income or salary analysis, the median is the far better measure. Why? Because if you analyze salaries with the mean, one massive extreme value from a billionaire will pull the whole average up, completely skewing your perspective. The median prevents this. On the flip side, for complex tasks like noise or error modeling, you'll actually often see the mean paired up with variance to get a complete picture.
Let's rapid fire through some heavy-duty practical examples, specifically in engineering and data analysis. The mean is the undisputed champion for creating baselines. Engineers rely on it heavily for finding average sensor measurements over time, performing signal estimation, baseline noise analysis, calculating expected values, and foundational statistical modeling. When the data is well-behaved, the mean is just incredibly powerful.
But, as we know, engineers don't work in a perfect world. They counter the chaos of the real world using the median's rugged toolkit. Because it's completely immune to sudden data spikes, engineers use the median for robust filtering, removing extreme outliers, and cleaning up GPS or GNSS errors. It's heavily used in fault detection too. If a sensor momentarily glitches out and outputs a massive error, the median simply bypasses it by focusing on the typical position of the data, rather than getting thrown off by that extreme numerical value.
And this brilliantly illustrates the real-world dominance of the median in chaotic environments. As highlighted in our sources, a median filter is widely used in signal processing because it suppresses sudden spikes better than a simple moving average. It is literally the ultimate spike suppressor, maintaining the integrity of the data even when random, massive errors try to pull the center way off course.
So we've thoroughly charted out the foundations of central tendency today, uncovering the fascinating differences between the highly democratic yet sensitive mean and the fiercely robust position-based median. They both seek the center, but they tell completely different stories about the numbers, which leaves us with an empowering and maybe slightly skeptical final thought. Next time someone tells you the average salary or the average cost of a house in your area, will you just settle for the mean, or will you challenge them and ask for the median?